Okay, this is our last day of learning new related rates problems, and hopefully you're feeling pretty good and that you got some good practice on your homework and you've gotten all your questions answered so far. Let's start with a warm-up to see if we're all in the same place. A cat is lying down 8 feet from the bottom of a wall, where a mouse is crawling straight down towards the bottom at a rate of 0.5 feet per second. At the instant when the mouse is 6 feet from the bottom of the wall, what is the rate of change of the distance from the cat to the mouse? So try this on your own. And if you needed some help, let's remember that we should first start by drawing a picture. In geometrical situations, I find it very helpful. So there's a mouse crawling down a wall, and there's a cat. So there's like a cat over here somewhere, and the mouse is crawling down a wall. The mouse is 6 feet from the bottom of the wall, but it's moving. So we've got this like y distance and this x distance here. Now, the cat is lying down 8 feet, and so this is a constant. This is not changing. It doesn't say the cat is moving. On the other hand, there is dy dt. Dy dt is negative 0.5, and it's negative because y is getting smaller. This distance is getting lower because the mouse is crawling down the wall. Now it says, what is the rate of change of the distance from the cat to the mouse? So y is 6 right now. So it's asking for the distance from the mouse to the cat. Now that distance is the hypotenuse of a triangle. The distance from something to something is always the straight line distance. And so this is a variable, and what we're looking for is dc dt. So here we have a relationship that says we've got some variables and some rates. The rate that we're given is dy dt. That's 0.5 or negative 0.5. We have dc dt, and that's what we're looking for. And so we need a relationship between c and y. And we have that, of course, because there is walls meet at a right angle, and so there is this Pythagorean theorem that we can use, which says that 8 squared, because this is a constant, plus y squared equals c squared. So 64 plus y squared equals c squared. And we're going to do d dt, the derivative with respect to time, on both sides to get a relationship between these two rates. We want a relationship between how are these rates related to each other, and so we need to take the relationship between the variables. So let's be clear here. This is a relationship between where the mouse is and how far apart the mouse is from the cat. So there's a relationship between the mouse's distance up the wall and the distance from the cat. When we take the derivative, that will be a relationship between the rate of change of the mouse and the rate of change of the distance between the mouse and the cat. So we do the derivative of a constant, that's 0. The derivative of y squared is 2y dy dt. We do have to use the chain rule there, equals 2c dc dt. Now we're going to plug stuff in. The y is 6 because it says at the instant the mouse is 6 feet down the wall. Remember, we could not put in that 6 initially because that would make it look like the y wasn't a variable, but now we can. dc dt is negative 0.5 equals 2. We need a number here because we need to solve for dc dt. So we need to know what c is, but it didn't tell us. So remember, we can always go back to the original relationship between y and c, and since we know what y is 6, we get 64 plus 6 squared is 36 equals c squared. So c is 10. So we'll plug in 10 for c. So c is 10, and we had to solve for that by plugging in 6 for y to find what c was at that instant. So let's see, we can multiply this out and we get negative 6 equals 20 dc dt, and we can divide by 20 on both sides and get negative 3/10, or negative 0.3 is fine. And let's use units. C is a length, so it will not be in any units squared. It's just going to be in feet per second. Okay. At that same instant, what is the rate that the area is, at what rate is the area changing in the triangle formed by the cat, the mouse, and the bottom of the wall? So we want the area of this, asking for dA dt now. So let's see how you guys do on this. How is the area changing? Well, so now the rate we need is dA dt. And so we need an expression with area. We also have some rates. We now have dc dt if we need it. We have, because we solved for it earlier, we have dy dt. And so we need how the area of the triangle is. And we should know that the area of a triangle is 1/2 the base times the height. Now the base is not x, the base is a constant. And so we put in 8, not x here, because the cat is not moving. So this distance isn't changing. It's really important to recognize what things are changing and what things are not. So 1/2 the base times the height, and the height is y. So the area is 4y, which is good because we have a relationship between the area and y, which will give us, when we do the derivative, the relationship between dA dt and dy dt. So dA dt equals 4 dy dt, and dy dt is negative 0.5. So dA dt is 4 times negative 0.5, which is negative 2. So dA dt is negative 2. Now, what are the units here? The units are its area. How is the area changing? And this area will be measured in feet squared per second. So this area, as the mouse is climbing down the wall, is changing by negative 2 feet squared per second. Okay, so let's get into some new problems. Gravel is being dumped from a conveyor belt at a rate of 10 feet cubed per minute. So what is this? Is this an area, a volume, the rate of change of the area, or the rate of change of the volume? Hopefully we notice that feet cubed is a volume, but it's per minute. So this is a volume, the rate of change of a volume. This is dV dt. So hopefully you're able to recognize that. So I can already put in my rates that I have dV dt. It's 10. And so I know the variable that will go with that is volume. And its coarseness is such that it forms a pile in the shape of a cone, whose base and diameter are always equal to each other. How fast is the height of the pile increasing when the pile is 8 feet high? So it's asking for how fast is the height of the pile increasing. This is dH dt. That's what we're looking for. And so we only have two rates. We have dV dt that they gave us and dH dt that we're looking for. We need a relationship between volume and height. Now, I told you at the end of last lesson what are the formulas you're supposed to know, the geometrical formulas. And one is a cone. You're supposed to know the volume of a cone. So hopefully you remember it right now. It's a great time to check yourself. The volume of a cone is volume equals 1/3 pi r squared times the height. And so what I notice here is I can't take the derivative right away because I'm allowed to have a relationship between the volume and the height, and I have volume and height, but there's also this r. And we're not allowed to have r in our equation because we would get, when we do the derivative, when you do the product rule, you'll get a dr dt, but we don't know what dr dt is. And so we'll get stuck. So instead, we're going to look for a way to get rid of r. We want to know what r is equal to be able to substitute. So what r is equal to? What is r equal to? Well, it told us here. It told us that the base diameter and the height are always equal. The diameter is equal to the height. Now, that's not the same as the radius being equal to the height. What is the diameter? Well, the diameter you're supposed to know is 2 times the radius. So we get 2 times the radius is equal to the height. And so we can solve for r. R equals 1/2 the height. We just divide by 2. The radius is half the height. And so we can plug in that the radius is 1/2 the height. And so this is r was being squared, so it still needs to be r squared times the height. I could take the derivative right now and use the product rule and the chain rule and a bunch of other stuff, but it's way easier if we simplify this. So how does this simplify? Well, we can square this, and I'm going to do this in a number of steps, although a lot of times we'll do, so 1/2 h times 1/2 h. 1/2 times 1/2 is 1/4, and h times h is h squared. And now I can multiply things together. A third times a fourth is 1/12. And I'm just going to go ahead and put the pi on top. So pi over 12. H squared times h is h cubed. Great. This is way easier to take the derivative of. So now let's do it. What is d dt of this? And we're going to simplify. So d dt, the derivative of the left side is dv dt, which is what we already know, equals pi over 12 times the derivative. It's a constant multiplier, so it just stays there. Times the derivative of h cubed is 3h squared times dh dt. Okay, so dv dt is 10, and I could simplify a little bit here, and I will in a minute. What is h? When the height is, when the pile is 8 feet high, so this is the height, so I can plug in 8. So let's see, 8 squared is 64, so I get pi times 3 times 64 over 12 times dh dt. And I'm going to divide by 3 and divide by 3. That will make it just be 4 on the bottom. And then 64 divided by 4 is 16. So I get 10 equals 16 pi dh dt. And I need to get dh dt by itself. So 10 over 16 pi equals dh dt. Real quick, I sometimes see kids try to change this into decimal, and they really mess up because they do 10 divided by 16 pi in a calculator. And this is wrong. This is not the right answer. It's 10 divided by, in parentheses, 16 pi. The whole denominator needs to be in parentheses if there's more than one thing. This is the right answer. So dh dt, what are the units going to be? This is 10 over 16 pi, which is a fine way to leave it. Or we can leave it as 0.199. We round to 3 decimal places in AP Calculus. So 0.199 or 10 over 16 pi, both are okay. And height is a length, so it will not be meters squared or units squared or anything. It's just a length, and it's going to be in feet per minute. So there we go. So similar deal here, except we have to draw a picture. We aren't given a picture this time. A cone has a height of 16 centimeters and a radius of 4 centimeters. So go ahead and draw that yourself. Make sure you feel good about it. Hopefully we got that there is a cone. Oh, it says the cone is vertex down. So maybe you might need to redraw your cone to make the vertex be down. I was going to draw it vertex up like the other one, but this says the vertex is down. And it says the cone has a height of 16 centimeters and a radius of 4 centimeters. Water is flowing into the cone. So there's like water at a rate of 2 cubic centimeters per minute. So what is this? What is 2 cubic centimeters per minute? Well, that is a rate that volume is changing. We know it's volume. This is dv dt. So we already know one of our rates. So rate dv dt. So we know we are going to need in our equation, we're going to need what variable? We're going to need volume. And dv dt is 2. Okay, how fast is the water level rising? So the water is not up at the top of the cone. The water is like rising. It's somewhere down here. And so there's a tricky geometry thing we're going to need to use in a second. How fast is the water level rising? What is this actually asking for? Well, it's a rate. How fast is it changing? And what is the water level? How fast is the water level? Well, the water level is like this height. It's like how high is the water? That's what the water level is. So this is dh dt. So it wants to know dh dt, and so we need h. So just like before, we need a relationship between volume and height. So what is the equation for the volume of a cone? Another try on this. The volume is 1/3 pi r squared times h. That is a formula you should know. Sometimes it gives it to you on the AP exam, and sometimes it doesn't. So, it really depends on how hard they think the problem is. Sometimes they'll give it to you, and sometimes they won't. Now, I notice that there is something that's going to give me a problem in this. What is giving me a problem? Well, there's an r here, and so if I took the derivative, I would have to use the product rule, but I would get a dr dt, and I don't have dr dt. So just like before, I need to say what r is equal to and substitute it in. But this time they didn't tell me like the diameter is twice the radius. Instead, we're going to make use of a geometry trick, which is that all the way up a cone, you should know that it makes similar triangles. So the ratio between the radius and the height at any given point, so like whether you're here on the cone, so this is like A and B, or you're like up here on the cone, these are similar triangles. So if this big triangle is C and this is D, A over B is the same as C over D. That ratio is the same. And so, so for instance, 4 over 16 is always equal to the radius over the height at any point. This ratio is always the same. These make similar triangles. Oh, you couldn't see that earlier, I'm sorry. These ratios, the ratio of the width to the radius to the height will be the same at any place. So even though the radius and the height aren't 4 and 16, because they're changing, because we're not talking about the whole cone, we're talking about where the water is, we know that that ratio will be the same. And so we can solve to get what the radius is equal to. The radius is equal to, and I'm going to simplify this, this is 1/4, and we multiply both sides by height. So 1/4 the height. Try it on your own from here. What is dH/dt? It's going to look very similar to the problem we just did. So we should have gotten 1/3 pi, and when we plug in the radius is 1/4 the height, and we got that because we know that from geometry that these ratios are the same. So 1/4 the height squared, because the radius, this is r, and r is being squared. We should simplify. So 1/3 pi times 1/4 h times 1/4 h is 1/16 h squared times h. I can simplify a bunch of things. 1/3 times 1/16, the denominators will multiply, and I'm going to move the pi on top. This is pi over 48 times h cubed. And so now I can do d dt. So dv dt, this is doing the derivative with respect to t on both sides, is equal to pi over 48 times 3h squared dh dt. This was a constant multiplier, so I just left it there. I can simplify a little. I can divide by 3 and divide, like multiplying by 3 and dividing by 3 will cancel out a little bit. And so this is pi over 16. And let's see. I need to plug in h. What is h? Oh, it tells me in this question over here. How fast is the water level rising when the water is 5 centimeters deep and 15 centimeters deep? So this is h is 5 and h is 15. And so hopefully you got dv dt equals, when h is 5, we're going to get 25 pi over 16 dh dt. And so, what was dv dt? dv dt was 2 cubic centimeters per minute, so this is 2. And so to solve for dH dt, I need to divide by this fraction. Dividing by a fraction is the same as multiplying by the reciprocal. So we're going to multiply by 16 over 25 pi. And so we get 32 over 25 pi. 2 is the same as 2 over 1. It just multiplies times the numerator. And dH dt should be measured in centimeters per minute, because the height is just a length. So it's measured as a length, not an area or a volume. If we did 15 centimeters deep, it would just change the height when we plug it in to 15 squared. The rest of the problem would be exactly the same, but we'll get a different rate. And so, I think we get 32 over 32 pi, or 32 over 125. No, 200. What am I doing? 225. 15 times 15 is 225 pi. And that just goes to show you that the rate of change really depends on where the water level is, and that should make sense. Think about it. When the cone is only a little bit deep and the water is flowing in at a constant rate, imagine like filling up a cone with water from a sink that's pouring out at a constant rate. Well, the height rises very fast at first because the cone is very narrow at the bottom. But as the cone gets wider and wider and wider, the height starts filling up less slowly because it takes more water to fill it up. So the bottom of a cone fills up faster, and then as it goes on, you end up with a slower rate of change, and that's what the calculus is telling us here, which is very nice. Okay, let's try another one. This is just another, these are like kind of the standard examples that get used in any calculus class. You would see them anywhere. A 6-foot tall man walks away from a 15-foot tall lamppost at a rate of 5 feet per second. After 3 seconds, how fast is the shadow lengthening? So, draw a picture, see what you can do, label your rates and your variables, and just take a pause on this, make sure you can get the setup right, and then we'll see how you did. Hopefully you drew a lamp post or something. This is 15, you didn't need to like draw a nice picture of it, but this is 15 feet high, and there's a man, it doesn't matter what side of the lamp post it's on, but there's a guy who's walking away, and he's 6 feet tall. So, you know, if we're just to draw it geometrically, we'd say 15 and 6, and they're both the same on the same ground, so maybe it looks like this. And it's talking about his shadow. Well, how do shadows work? Well, the way shadows work is light comes out of a lamp and the guy blocks it. So the way, like, okay, this part, anything that is like to this side of him will be light because the light from the lamp will shine on it, but he's like blocking everything in here. And so that's what a shadow is. It's the light that gets blocked off from him. So this is the shadow. And as he walks away, apparently, let's see, he walks away from the lamppost at a rate of 6 feet per second. So or 5 feet per second. So what is it that's changing 5 feet per second? What's the distance between him and the lamp? And I'm going to call it x because it is a horizontal distance. And so what we have, our rate is dx dt, and that's 5. X is getting longer as he walks away from it. And so x will be part of our thing, probably. That's one of the variables we can use. And now it's asking how fast is his shadow lengthening. So I guess I should use this length right here between the guy and where the light stops getting blocked off. I'm going to call that S. Man, I hate using S's in problems. They look like 5s. So there's so many 5s in this. There's a 5 here. There's a 5 here. That S is going to cause us trouble. I'm going to use a script S, a cursive S. I'm going to use an S like this. Okay. That's going to be my variable. So it's asking us for ds dt, which is, so the variable then is S. So I need a relationship between S and X so that I can, when I do the derivative, I'll get dx dt and ds dt, and I can find the relationship between their rates. So think about geometry for a second, and what relationship do we have here? Well, I hope that we notice that there are similar triangles, that this triangle is similar to the large triangle. And so, you know, when we have similar triangles, the ratios are proportional to each other. So like I have this and this, so this side is to this side, so the small height is to the big height as S is to what? And I will tell you, sometimes kids put X and it's wrong. The little length, so this is the length of the base of the little triangle. The length of the big triangle is not X. X is from here to here. It's X plus S. Because it's this length plus this length, that's the whole length. So be a little careful there. I'm going to simplify this. I don't want to do the quotient rule, so I'm just going to multiply out the fractions. So I'm going to multiply both sides by x plus s. And I'm going to multiply both sides by 15 also. So multiplying by 15 and dividing by 15 cancels out. Multiplying by x plus s and dividing by x plus s cancels out. 6 will multiply times x plus s and give me 6s plus 6. Oh, I should have put 6x first. Equals s times 15 is 15s. My s looks a lot like a triangle. Get over it. You guys can subtract 6s on both sides to combine nicely. And now we've got a relationship, a really easy relationship between x and s. And so now I can find the relationship between dx dt and ds dt by doing the derivative on both sides. So d dt. And now I get 6 dx dt equals 9 ds dt. And what did I know? I knew that dx dt was 5, so 30 equals 9 ds dt, and so 30 over 9, which is, we can divide by 3 and divide by 3, this is 10/3, is ds dt. So as he's walking 5 feet per second, his shadow is getting longer by 10/3 feet per second. Now, a slightly different question that we could ask is, how fast is the tip of his shadow moving? S is the length of his shadow. That is not this. Here's the tip of his shadow. How fast is it moving along the ground? Well, it's not just how much is it getting longer, because he's also moving. He's moving and his shadow is getting longer. They're both happening, and they're actually making his shadow tip move faster than he is. If you ever walk away from a light source, you'll notice that your shadow is actually moving slightly, the tip of your shadow is moving slightly faster than you are, because it's both getting longer and you are moving away from the light source, and so your shadow is moving extra fast. So what represents, what could I use to represent where his shadow is? Well, where his shadow is x plus s. So we want the derivative with respect to time of x plus s. This is like where his shadow is, and we want to know how is that changing. So we just do the derivative with respect to time, and we get dx dt plus ds dt, both of which we already know. Dx dt is 5, and ds dt is 10/3. And if I wanted, I could make this into 15/3, multiply by 3 over 3, so I can get a common denominator and get 25/3. And this is going to be measured in feet per second because it's a length. So that's it. So we feel okay about that. All right, a new kind of problem. A plane flying at a constant altitude of 4,000 feet, and altitude is a height above the ground, is flying west at a rate of 700 feet per second. Here we have a rate. A searchlight under its path tracks it, so there's a light tracking it. How fast is the angle of the light, angles, here we go, changing when the plane is 100 feet east? Draw a picture of this. Take a minute and try to draw what is happening here and see how it compares to my drawing. Okay, so there is a plane. Okay, here's my plane. I don't know. That's a plane, guys. And it's flying west. West on a map is usually left, like California is west. And it's flying at a rate of 700 feet per second. So I'm going to put my, this is, I don't even know what it's a rate of yet. So I'll hold off. I've got 700 feet per second. We'll figure out what is actually changing, what length is actually changing 700 feet per second. And there's a searchlight under its path. A searchlight is something that like shines a light up at the sky. Think of like the bat signal up in the sky, or if you ever pass by, like every once in a while there'll be like car dealerships that'll like shine a light up at the sky. They used to use them in World War II to like shine a light on a plane so that like when bombers were coming in, they would shine a light so that their planes could go try to shoot them down. So there's this like searchlight shining on the path, and the searchlight is changing over time. Now I drew it with the plane to the left. Oh shoot, I drew it wrong. Okay, I'm gonna draw my searchlight over here. I thought I was reading it right, but I read it wrong. So sorry about that. It said when the plane is 100 feet east. So I know the plane is 100 feet east of the searchlight, and that is a straight line distance. So this distance is 100. Now, is that a variable or a constant? Well, the plane is moving, so this distance will be changing. Instead, I should use x for it. Okay, when the plane is, and the plane is flying at a constant altitude of 4,000 feet, that's the height above the ground. And we can see this makes like a triangle here. Now this is 4,000. Now is that a variable or a constant? Well, the plane is flying at a constant altitude, and so its height isn't changing. But this distance is changing, okay? And it's asking about the angle of the light. So as the plane is moving, the light has to change. So like when the plane is over here, the light is obviously going to be shining at a different angle. So we're talking about this angle, and I'm going to call it theta. And so we have a triangle with an angle. So as that plane is moving, when the plane gets to a new spot, the searchlight is changing, and so this angle is changing. This height is not changing. So like at another spot, over here, if we were looking like back in time, this distance would be much larger and the angle would be lower. See how this angle is lower than this new angle? So as the plane is flying this way, the angle must be getting bigger. So I can kind of see that d theta dt is going to be positive. And that's what it's asking for. How fast? So d theta dt is one of the rates. That's what we're looking for. And so I know I need to have theta in my equation. And the rate I have is dx dt. I can now see that this is changing. So dx dt. And dx dt is actually negative 700 feet per second. This length is getting smaller because the plane is to the east, but it's flying west. So if it's flying this way 700 feet per second, this length is going to get shorter 700 feet per second. And so I need a relationship between x and theta. And what I can have in my equation is any constants. What I cannot have is another variable. So I've got this side is x, and that's clearly changing. The height is not changing. What about this? The hypotenuse, is that a constant or is it changing? Well, I hope we know that as like think about this other place right here. As the plane is moving, this hypotenuse length is clearly very different than this hypotenuse length. The hypotenuse is changing, and so this is a variable. And so when I come up with my equation, I want to have a relationship between x and theta, but I can't have c in it because I don't have dc dt. So I need a relationship between x and theta, and I'm allowed to use this constant if I want. I hope we recognize that we can use a trigonometric identity to say that, I can do like opposite over adjacent or adjacent over opposite. And that's what I'm going to do. I'm going to say tangent of theta is equal to the opposite, which is 4,000, over the adjacent, which is x. So this is a relationship between the angle and x. Okay. I also could have just as easily used cotangent of theta equals x over 4,000. And this might have actually been better because this is a constant divider is the same as a constant multiplier, and it makes the derivative easier. Whereas here we have you're dividing by x, and so we need to use like the power rule or the quotient rule or something. So I'm going to go ahead and do this one just because I think this is more likely how kids set this up. So this is d dt, and the derivative, what is the derivative with respect to both sides? Well, the derivative of tangent theta is secant squared of theta times d theta dt. Here we have 4,000 over x. This is 4,000. You could do quotient rule, but this is easier to be done as a power rule. This is x to the negative 1 power. So I'm going to multiply by the power and lower the power by 1. So it's now over x squared. So the power becomes x to the negative 2, which is over x squared. Oh, times dx dt, because I'm doing d dt and I did the derivative of x. So the derivative of x to the negative 1 is negative x to the negative 2 times dx dt. And let's see, I need to solve for d theta dt. So dividing by secant squared, secant is 1 over cosine, right? And so dividing by 1 over cosine is the same as multiplying by cosine. Dividing by a fraction is multiplying by its reciprocal. And so d theta dt equals negative 4,000. I guess I should start plugging in. What is x? X is this distance, and it says when the plane is 100 feet east, so 100 squared times dx dt is negative 700. And then we multiplied by cosine squared on both sides. So cosine squared of theta. Now, what is cosine of theta? Cosine is the adjacent over the hypotenuse. So I guess I need to go find when x is 100, what is this? So I need to use the Pythagorean theorem here to solve for what c is, because to do cosine, it's going to be x over c, adjacent over hypotenuse. And so cosine squared is going to be 100 squared over whatever this is squared. So let's see, 100 squared plus 4,000 squared equals c squared. I don't want to do this, guys. Oh, this is so ugly. Let's use a calculator. So 100 squared plus 4,000 squared, that's c squared. So c is the square root of 1601,0000. Okay, cool. And the reason I'm not going to simplify this is I know I'm about to square this in a second, because it says I'm going to do cosine squared. I feel like I messed something up somewhere. Hold on. Okay. So cosine is the adjacent over the hypotenuse. So this is 100 over the square root of 1601,0000, and we square it because it's cosine squared. So that'll cancel this out. I don't really want to multiply this all out, but I will. Negative 4,000 divided by, I need to put it in parentheses, 100 squared. That has to go in parentheses. Times negative 700 times 100 squared divided by 1601,000. Okay, and so there it is. D theta dt is 0.175. And I believe it's in radians per second. Okay, cool. Great. So these are tricky. Let's see how you do on one on your own. An airplane flies at an altitude of 5 miles due west towards a point directly over an observer. So here's the observer. The speed of the plane is 600 miles per hour. Find the rate of change at which the angle of elevation is changing when the angle is pi over 6. So try this one on your own. Try to set it up. You probably will struggle on this, and that's okay. But try it on your own. So let's see. Let's label what we can do. An airplane flies due west. The speed of the plane is 600 miles per hour. So that's, I'm going to call this x. So dx dt is going to be negative 500 or negative 600. And so I know x is going to be my variable. Find the rate of change at which the angle is changing. So once d theta dt, that's what we're looking for. When theta equals pi over 6. Okay, so I need a setup between x and theta. And is there a constant? Yes, there is a constant. Does it tell us what the height is here? Oh, yes, an altitude of 5 miles. So this is 5. Great. So this says 6,000. It should say 600. I wrote an extra 0 there. Okay, so similar to before, I hope you set up your equation as we can do, if we only want to have theta and x, we can only use these. We can't use c, which is changing. So you can do tangent of theta equals 5 over x, or maybe you could have used cotangent of theta equals x over 5. Either way is fine. When you do the derivative, I'm going to do this one. The derivative of both sides with respect to t is the derivative of tangent theta is secant squared of theta, d theta dt, equals, this is 5x to the negative 1. So when we do the power rule, it'll be negative 5x to the negative 2, I guess, over x squared times dx dt. And just like before, we're going to multiply by cosine squared to get rid of the secant squared. So secant squared is 1 over cosine squared. We're going to multiply both sides by cosine squared to get rid of it. So d theta, that's another way of thinking about it slightly different than what I phrased last time. So it's going to be negative 5 over, okay, now we don't have what x is. Okay, so we'll get to that in a second. Negative 5 over, we need to solve for what x is. So tangent of theta is 5 over x, and theta is pi over 6. So we can do tangent of pi over 6 equals 5 over x to solve for x. Oh man, what is tangent of pi over 6? I actually don't know my tangent values. I just memorized the sine and cosine, and I know that sine over cosine is tangent. So pi over 6 on the unit circle is the little one. And so sine is 1/2, cosine is square root 3 over 2, and so when I divide, I multiply by the reciprocal, and, oh wait, hold on, multiply by the reciprocal, 2 over square root of 3, and so we get 1 over square root of 3, which is root 3 over 3. So, okay, so root 3 over 3, that's your tangent value you should know from pre-calculus, equals 5 over x. I'm going to multiply by x and divide by this. Man, I wish I had not done this. I made a poor choice here. I'm just going to leave this as 1 over, so 1 over square root of 3, because it'll work out easier when I actually multiply. So I'm going to multiply by x on both sides and multiply by square root of 3 on both sides, and x equals 5 square root of 3. So x is 5 square root of 3, and so x squared is 5 square root of 3 times 5 square root of 3 is 25 times 3. Whew! Okay, that was a lot of work. Times dx dt. Do we know what dx dt is? Yes, negative 600. Times secant squared of theta. Hey, sweetie, did you wake up from your nap? Okay, I'll be with you in just a minute. Okay, I need to finish this video. Okay, I'll be with you in a little while. Where were we? Okay, 5 times this, and then we needed to do cosine. Okay, so we multiplied by cosine, so we need to do cosine squared of theta. What is cosine? Cosine is adjacent over hypotenuse. Oh, but we haven't found the hypotenuse yet. We found x was 5 squared of 3. We can do the Pythagorean theorem to find what this is. So a squared plus b squared equals c squared. Let's see, this is 75 plus 25 equals c squared, so c is 10. Okay, so cosine then is the adjacent, 5 square root of 3, over the hypotenuse, which is 10, squared. Okay, and boy, a lot of stuff is going to cancel out. This is going to be negative 5. I'm going to do a lot of this times 75 times negative 600 times 75 over 100. So the 75s will cancel out, the 100 will cancel out with the 600, and we should just get 30. So the rate of change of the angle is 30, unless I messed something up. I don't know, I very well could have. So that's d theta dt, 30 radians per second. Okay. All right, last problem. A ladder 25 feet long is leaning against the wall of the house. The base of the ladder is pulled away from the wall at a constant rate of change of 2 feet per second. Go ahead and draw a picture of what's going on. Hopefully you got that there's a ladder that is a constant. The ladder won't be changing, but it's going to be being pulled away from the wall, and so x will be changing and y will be changing. These will both be variables. And we have our rate that it gives us is dx dt is 2 feet per second. So we know we'll have x in there in our equation. Consider the triangle formed by the side of the house, y, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So when x is 7, what is this? So the area of the ladder, the area is 1/2 the base times the height. And these are both variables. I can't plug in a constant for either one of these. They're both changing. This is being pulled away, and as this pulls away, this will be coming down. So they're both changing. Now, it wants the rate of change of the area. It wants dA dt, but I can only have a and x in there. I can't have this y. So I need a relationship. I need to get rid of the y, and for that I need my Pythagorean theorem. We did this yesterday. So x squared plus y squared equals 25 squared, which I think is 625. And so I can solve for y. Y is 625 minus x squared, and I need to take the square root. So that. So the area is 1/2 x times the square root of 625 minus x squared. Great. We can take the derivative of both sides and get dA dt equals, this is a product. The derivative of the first is 1/2 dx dt times the second one left alone. Plus, I leave the first one alone, so 1/2 x times we do the derivative of the second, and this is a chain rule thing. This is 625 minus x squared to the 1/2 power. So it'll be times 1/2 times 625 minus x squared to the negative 1/2 power. I have to lower the power by 1. So that'll go in the denominator, 625 minus x squared, times the derivative of the inside. And the derivative of the inside will be negative 2x dx dt. So times negative 2x times dx dt. And I can probably just plug in already. So 1/2, what was dx dt? 2 times 625 minus, what is x? 7 plus 1/2, x is 7, times negative 2 times 7, and dx dt is 2 over 2 times the square root of 625 minus 49, because 7 squared is 49. Okay, just doing some quick math. I believe this comes out to be 24 plus, and I might be wrong about this, 24 plus, okay, cancel this, cancel this, cancel this, cancel this, cancel this, cancel this, minus 1 over 24, I believe is what it comes out to be. So it'll be like 23 point, I don't know, whatever, 24 minus 124 is. 24, I think the answer comes out to be 23.958. What was this? This was dA dt. And so the units of this will be measured in feet squared per second. Feet squared because it is area, and it was changing in feet per second. What's going on? Find the rate at which the angle between the top of the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. Whew. So we got that same situation, right? The angle at which the top of the ladder from the wall, so this angle is changing when the base is 7. So same thing, but now we're looking for d theta dt, and we have dx dt still. So we want theta and x. So we need a relationship between x and theta, and here we're not allowed to use y because we don't know dy dt. So we need a relationship between x and theta. This is the opposite and the hypotenuse. So the opposite and the hypotenuse, that's going to be sine. We need to use sine here. Sine of theta is equal to x, the opposite, the across from it, divided by the hypotenuse. And this is a fairly easy one to do the derivative of. The derivative of sine of theta is cosine of theta, d theta dt. The derivative of x over 25 is just 1/25 times x. Like, this is a constant multiplier. This is a constant divider. It's just going to be dx dt over 25. So d theta dt is what we're looking for. So d theta dt equals dx dt, which was 2. And we have to divide by cosine of theta. So times, dividing by cosine is like this. Or we could do secant of theta. Cosine is adjacent over hypotenuse. And so 1 over it will be hypotenuse over adjacent. The hypotenuse we said was 25. So we get 2 over 25 times 25 over, what is the adjacent side? Well, the adjacent side is y here. We know what x is. We know what the hypotenuse is. We can use the Pythagorean theorem here. So there's a lot of geometry in this unit. So we get 7 squared plus y squared equals 25 squared. Y is going to be the square root of 625 minus 49, which is 24. The 25's cancel. We can divide by 2 and divide by 2. This is 1/12. So here, d theta dt is 1/12. I went over, oh, you guys couldn't see this. I was multiplying this times the hypotenuse over the adjacent. The hypotenuse was 25. The adjacent side we found by using the Pythagorean theorem. And that's it, guys. That's it for new related rates. Feel free to get some help. You will get some more practice in your homework tonight.